As an extension of the neutrino circuits, there might be the sterile neutrino, which can argue that the several anomalies in the neutrino experiment and also the important role in the cosmology. The sterile neutrino can be the candidates to the dark matters, but to explain the dark matter abundance, the enough abundance of the sterile neutrino is necessary, so the production mechanism is important. Today I want to talk about how the star neutrino can be produced in the early universe and also the other cosmological remarks on the active and the star neutrino. The Lagrangian for the neutrino mass can be written by the two terms. The first one is the Dirac mass term arising from the Higgs bob in the Yukawa coupling form. Then the other one is the Manara mass term. And the in the typical scenario, the total neutrino capital R is produced by the active stellar mixing, which is suppressed by the ratio between the Dirac mass and the Manara mass term. And this mixing angle is extremely small, so that this requires the other production mechanism to explain the abundant dark matter. There are two well-known mechanisms. The first one is the Donaldson withdrawal mechanism. This adopts a non-resonant oscillation. In the early universe, we need to consider the thermal effect with the temperature dependence. The Boltzmann equations for the following momentum of distribution in the dependence of the momentum p. This is the following. The left-hand side is just the time derivatives and the momentum derivative for the distribution function. On the right hand side, there is a contributions from the decay or scattering. So here's the gamma, the momentum dependence, the decay light, and there will be the mixing angle terms will be added, and this mixing angle should be applied to the matter effect, so-called MSW. So in the early universe, there's no vacuum. The stellar neutrinos propagated in the medium, so the potential contributions will be added in the mixing angle. So this sin square 2 theta is the mixing angle in the vacuum, and we need to add the potential contribution. Plus over the Vt is the contributions from the finite temperatures, and the VL is the Lapton symmetry. But in the Donaldson withdrawal mechanism, the Lapton symmetry potential is just attributed 0, so there's no resonance effect in here. And the delta, which is the mass scale difference over the momentum, and in the such a Donaldson withdrawal mechanism and the star neutrinos as a dark matter candidate, the scale of the this Harvey neutrino is a kiloelectron volt. And then there will be the additional terms coming from the collisions, which is given by the decay term, and this decay light is given by the multiplications of the Fermi constant G ups, and by the dimensional analysis, there will be the T to the 5 powers will be multiplied. So there is a two regime in the high temperatures. The important term is the high temperatures. In the important term is the decay light in the Boltzmann equation. This one. But in the high temperatures, the effect of the finite temperature potential is large, which makes the medium mixing angle become small. So this term becomes small. But in the small temperatures, in contrast, the decay light becomes small, but the final temperature potential effects become small, so the mixing angle can be large, and there are no resonance here. So we can make some specific moment, which is both the decay light and the mixing angle in the medium become large. So there will be some peak moment from specific temperatures, At that time, the right-hand size of the Boltzmann equation becomes bigger, so the production of the sterile neutrino is enhanced, and this can explain abundance for the dark matter by solving the Boltzmann equation. But the problems of the distortion Neutrino mechanism is it is constrained tightly by the structural promotion through the X-ray. But still, the subdominant star neutrino dark matter is still viable. The other possible one is a Shibboleth's mechanism. In this case, the resonant oscillation is adopted in, and now the Laplace symmetry potential is non-zero. So in the medium mixing angle for the MSW, we can satisfy the resonant condition. So this term can be the J, which enhance the mixing angle. So such unstable resonance makes the mixing angle become large. And similarly, there will be some resonance temperatures around 100 MeV correspond to the QCD approach. Also, this can explain the killer electron volts to neutrino dark matter. Similarly, this can be constrained by the X-ray. Star neutrinos decay to the active neutrinos around the bottom, and the broken and analysis correspond to the X-ray. And such a star neutrino dark matter can make some specific structures like as a Lyman alpha in the small scale power spectrum. Also, we can consider the high temperatures and the low temperature regime as this Shibboleth mechanism. If we adopt the variables y, which is defined by momentum over the t, in high temperatures, these variables become small, but in some specific moment, there will be some resonance moments for this y. But in the low temperatures, the spectrum is cold due to the universe cooling, so that we can analyze some productions of the star neutrinos and the Boltzmann equations through the different temperature regimes for the Shibboleth mechanisms. Also, there is the other production channels. If we add the additional particle like as a heavy field, then the decays or the scattering of this new heavy particle can produce the star neutrino. And also we can adopt the electron volt star neutrino, which is the so-called 3+1 regime to explain the several anomalies in a neutrino experiment. This electron volt star neutrinos eventually affects some cosmological observable. For example, it activates the number of neutrinos through the summation of the active neutrino one. Such anifactives and the summation of the amnews as important parameters of the BBN, CMB, or baryon acoustic oscillation. Such electron volt star neutrino can be tested by the short baselines in the neutrino oscillation experiments, and this can be produced in the thermal cell impact. And also there are other model, so-called the neutrinos minimal standard model, NUMSM. In this case, there is the 1 kilo electron volt dark matters, but there is additional 2 nearly degenerated GeVs heavy neutrinos leptons. Such a GeV channel has an important role in the ALS leptogenesis, which is the leptogenesis via the oscillations. There's a serious problem in here. How can I fix that? Maybe I can capture it and go to my gallery here. Yeah, here, and okay. Maybe I can rotate this like that. How can I rotate it? Yeah, maybe that one. And okay, complete. And yes, maybe I can draw something by using this. Okay. So continuing there's such a neutrino minimal standard model, NUMSM. There's 1 kilo electron volt dark matters. This is produced by the Shibboleth mechanism, and it gives the X-ray signal. And the 2 nearly degenerated GeV scale H channel N2 and N3 makes the leptogenesis via the generation. Now we turn to some active neutrino, so-called neutrino free streaming in the early universe approach. The active neutrinos that decouple in the mega-electron volt scale by considering the interaction light with the Fermi constant and the Hubble light. But after neutrino decoupling, the neutrinos propagate over the space-time of the universe, and they might have the no collisions or scattering. This can be parameterized by the free-streaming length. Such a free-streaming length is strongly correlated with the velocities of the neutrino. Such lambda fs is defined by the travel distance in Hubble time, the specific scale of the universe expansion. So this is just a distance. So such a travel distance can be obtained by the velocities times some specific time, and this time scale is given by the Hubble times 1 over the AITs. So and in the case of the relativistic neutrino, the velocities of the neutrinos are given by just the speed of the light. So the free-streaming length becomes the c over the IHs, and we observe that c equal to the 1 in the natural units, so just reduces to 1 over the IHs. But in the non-relativistic neutrino, there will be the mass effect. The velocity sort of becomes smaller than the speed of the light, and now the velocity contains the effective neutrino mass term. So in the numerator, there is a V with the mass dependence term. So neutrinos turn to the from the relativistic one to the non-relativistic in the light universe. In the CMB, the temperature universe is around the electron volt, and such non-relativistic transitions occurs to the when the temperatures of the universe is cooled down to the neutrino mass scale. This is around the sub-electron volt. In the parameters of the last step jet, such non-relativistic transitions occurs in the order of the 100. And in this case, the formula for the free-streaming length turn to the one of the H's, the V over the IHs. So the free-streaming length becomes shorter than the relativistic approach. In the today, if we insert the scaling factors and the Hubble parameters with the current value, then the scale of the free-streaming length is around 100 megaparsec. Yes. So such a last shift can be obtained by this formula. So the right-hand side is the neutrino mass, and the temperature of the neutrinos that reduces in the one of the eyes, and by the definition of scaling factors, we can obtain the non-relativistic transitions last effect of the scale factors. During the relativistic free streaming, especially at the radiation matter cyclicity or the combinations, at that time the last effect is 3,400 around temperatures around the electron volt. If we compare the neutrino free streaming length with one of the H formula, this is order of the 100 megaparsec. And because this scale of the 100 megaparsec of the free streaming length scale is longer than the CMB acoustic scale, this makes a very important role in the observable. For example, if we add the new extra radiations in the new physics model, then this makes the effective number of the neutrinos and EF becomes large, and such large NEF antibactives will make the fast expansion in the radiation dominant, because the such large impact mean that the contribution of the radiation becomes large, and this means the before the recombination, the time period become the short. So the sound horizon, the sound horizon becomes smaller than the neutrino free streaming length. Compared to the standard scenario, and eventually this affects the CMB acoustic peak or height. So by the testing the observes the CMB anisotropy or power spectrum, we can test the ineffective. So this effect comes from the relative size of the acoustic scale and the neutrino free streaming. And also the such a neutrino free streaming generates the anisotropic thrust, and also the modifies the CMB peak. In the point of view of the large scale structures like the galaxy cluster or power spectrum, because the GeV scale of the cold dark matter is very slow, so it means that the velocity is small, so the breathing length of the such cold dark matter is negligibly small, just as you. So such a slow velocity and the short and the negligible breathing length mean that the cold dark matter is always cluster. But the cases of the active neutrino with the electron volt scale, this becomes hot dark matter. Previous one, the star neutrinos through with the kiloelectron volt correspond to the warm dark matter. So electron volt scale of the active neutrino has a burst velocity, and the breathing length is the 1 megaparsec. This is a non-relativistic case in the current values by considering the mass bond. So compared to the cold dark matter, the active neutrino has a burst velocity and a non-negligible breathing length, and the clusters of the such hot dark matter require some specific condition. So the active neutrino cluster, when the scale of some specific structure is larger than the breathing length. So if that scale is larger than the breathing length of the active neutrino, then this can be cluster, because the neutrino cannot move or go away from the specific structures, the clusters of that. But if the galaxy scale is smaller than the neutrino free streaming length, then such a hot dark matter active neutrino does not cluster. So this makes the small scale power spectrum has a suppression. But by the observation, we know that there is some specific structures in the small scale, and this means that we can constrain the neutrino free streaming length. This neutrino free streaming length is strongly correlated with the velocity, and this velocity is also the dependence of the effective neutrino mass term. This means that the suppressions of the small scale power spectrum can constrain the summations of the active neutrino. This is a very important point. And in the large scale, this is automatically larger than the neutrino free streaming length, so there is no such as suppressions. So today we talk about several topics in the neutrinos in the point of view of the cosmology. The first of all, we discussed the two mechanisms for the sterile neutrino productions. The first one is the Dalton withdrawal, and the second was the Sipilus. both of them adopts the MSW effect, but only the C-pilot mechanisms adopts the resonance effect by considering the non-zero optimal symmetry potentials. And they can be constrained by the X-rays or the structures one. And also there are models called new MNSM over the killer electron board sterile neutrinos as the candidates of the Archimedes. We can ask the two nearly degenerate Gibbs scales of the H channels, which can realize the ARS leptogenesis via the relations. And lastly, we discussed that the active neutrino blistering length. This is defined by the distance over some specific time scale. And when the neutrino turn to the non-relativistic one, we should consider the effective neutrino mass. If we add some extra radiation components in the new physics model, this affects the sound horizon compared to the neutrino free streaming length, so that eventually changes the shapes of the CMB. In this pointy sort of the power spectrum, such active neutrinos that are hot dark matters cannot be clustered if the scale is smaller than the neutrino blossoming length scale. This makes the small scale suppressions in the power spectrums and can constrains the active neutrino mass. So such both the sterile neutrinos and active neutrinos has important role in the cosmology, also the early universe and in the later universe, like as large scale structures.